Cool. So yeah, so this section, which I actually can't even remember what the name of this section is, but basically it's all about probability, conditional probability. I think the title is, what's it say, combinatorics. I can't even remember what it reads, but basically, like, we're going to talk about a lot of conditional probability, Bayes' theorem, partitioning, basically like how probability goes through. And I like always like to say is like probability is just counting. But counting just turns out to be really hard, or at least can be very complicated. And so a lot of probability just ends up being like saying what events happen in certain event spaces. And so that's kind of like the curriculum goes through, walking through essentially what conditional probability is, and then going into saying, well, what's the law of probability? How can we partition these parts out, basically break it down so it's easier to like figure parts out. Because a lot of probability is based on just seeing what's there, you know, like for example, if you want to see what the likelihood of flipping a heads or tails on a coin, what you do is you flip a bunch of times and see what happens. And so this obviously has some, a lot of like weaknesses, because for example, if you only flip like 3 times and you get heads each time, you know, it might be that the coin is, you know, rigged where you only get heads every single time, or it could be something else that you just don't have enough samples in your, basically in your space. Basically you keep like flipping it, and if you flip it more and more, you're more likely to see the actual probability overall. But then it also relies on some assumptions and stuff like that. So there's a lot of things like in probability where we'll say like, oh, we need to assume these things, but for the most part we can assume a lot of them. But it's always should be in the back of your mind when you're using these tools, saying, hey, can I actually apply these tools to my situation? And sometimes you can't, but it has to be, you have to know that ahead of time. And sometimes the assumptions are broken, but they're so minor or they get muddled out that we don't really have to worry about them. We'll talk about that in a second. But one big strength about probability in general, which is why we'll talk about Bayes' theorem, basically is that you can use probability to tease out a lot of extra information. As you get more and more information, you can kind of figure parts out, and you don't have to know the underlying like reason for it, which of course can be a danger at the same time. But like the idea is like, you know, when you flip a coin, you guys intuitively know it's probably 50-50, right? But you don't need to know the complicated physics and fluid dynamics and flipping it over and everything like this to figure out, is the coin 50-50? You can just basically keep flipping it and figure out what it is. And that's kind of like where data science, I think, really comes into play, where you can actually use, what's it called? You can use events to tease out meaning out of something that you might not know the underlying, like I say, like the underlying theory, because it might be very, very complicated, or it might not really exist in a nice, easy form. So that's something to kind of keep in mind as we're kind of going into this probability, is saying like, how does this relate directly to data science? And a lot of this ends up being, a lot of our methods we'll find are using probability and randomness with our machine learning models and stuff like that, because you have large amounts of data and you're trying to figure out how to like process it. And it just turns out that if you try to like we saw way before, I think earlier in this section, this module, like one of the first 2 sections, you could try to solve systems of equations, right? We can perfectly solve these things, but to do it for a very, very large number of variables, it gets increasingly slow. And that's when we start doing other techniques to try to figure out like, well, we can have a strong computer that can do things very, very quickly. But if we try to do everything perfectly, it'll just take way, way too long. So there's kind of methods we go through. So again, this is kind of like framing like why we talk about this stuff and where it's going to lead us to. Okay, so let me go ahead and share my screen. And cool. No, oh, there we go. All right. So you guys can all see my screen, hopefully. Yeah. Cool. All right, awesome. So I'm kind of like doing a quick summary stuff, and like I've said before, I have this on GitHub. I don't think I pushed this yet, but if you guys go to the GitHub repo that I showed you guys know what I'm talking about, right? Cool. So I should have it up there sometime today if I haven't pushed it yet. But anyway, the first thing we need to talk about for probability is just conditional probability. And conditional probability, basically, you can think of it like it's putting a condition. So we've seen probability like flipping a coin, just like heads or tails. I mean, you can describe anything in probability by basically measuring a bunch of things. And so we talked about sample spaces before, but just as a reminder, our sample space is basically all the different kinds of events. And so a lot of times you actually see this like visually drawn out, is it'll be literally like a rectangle, and it's like, oh, this right here is a sample space, you know, and sometimes they'll say like S. Sometimes I think the curriculum actually uses a capital omega as a sample space. So you'll see this symbol, but basically it's just anything that can happen, Okay, which makes sense. You're kind of like, okay, like that's just, I don't know, sometimes I feel like in probability and sometimes mathematics in general, it feels like, well, duh, right? Like, of course, sample space is just everything that can happen. But it's really important to know ahead of time what are the possibilities and stuff like that. Because if you don't see a possibility, it might mean that you just don't have enough data samples to capture that event versus something where it's literally impossible to have. But of course, if you're doing like a pure pure data-driven part and you have no sense of what the underlying theory could be, then you might miss part of the sample space. So you always have to consider that thing when you're looking at your data. For example, if you're looking at like a data where it's like, okay, like their ratings for Yelp reviews go from 1 to 5 or something like that, but you only see 1 star, 2 star, 3 stars, and 5 stars, but you never see a 4 star. You're like, you know, technically it's like, oh, in my sample space, 4 doesn't exist. But obviously, you know, like, well, Yelp works, you have a 4 in there. So you have to always kind of consider those parts, okay? But anyway, sample space usually represented as like an area, and you can think of it, usually it's labeled as sigma. Sometimes I've seen it as capital S, but not sigma, sorry, omega. And so you can kind of think of either one of those. And the curriculum uses omega particularly. Hey, and then you'll see things like a point in here, like any single point, right, would be an event. And I'll usually list it as E. You know, some people can call it like A or B or whatever specific like event happens. And I guess I should technically, you'll usually not see a capital E. You'll usually see like lowercase e for a specific event, or lowercase a. Usually we use lowercase as like a specific thing that happened. And you will see this notation like the event, and then you'll see this weird kind of E thing in this sample space. Okay. And this basically is just saying it's E is an element of this set. This is like, this little weird E is actually an epsilon. Well, it's like an epsilon, it's not quite. But usually it's saying that it's an element of, it belongs to this. It's inside of this set, this sample space. So again, some notation so you kind of are familiar with what's going on, right? Any questions on that? Just some general notation? Okay, cool. Yeah, so now if we're going into, sorry, oh wait, am I looking at the right one? Oh, sorry, yeah. I shouldn't put independent and dependent variables. I don't know why I put that. It should be independent and dependent. Because we're not talking about variables in general. We're talking about events, right? So you'll notice here, like in the curriculum, we'll talk about like A and B, and you can think of A and B as like actual like many different events. Usually we'll talk about it as a specific one event, but you can think of it as a grouping of events that are like, oh, all the things that are A and all the things are B. So for example, a simple one would be A is heads and B is tails, that kind of stuff. Or it could be something like, you know, if you go into a medical test, this is a classic one for Bayes' theorem. You go get a medical test, you test positive or you test negative. Those would be different events, either A or B, but it could be also grouping events. So the way we usually draw this actually in, visually, and this is how it's usually shown, is you'll have an event space or a sample space, S, or not S, we'll call it omega, right? And then you'll have something like, these are all the events A, and these are all the events B. Okay. And again, we'll write them capital too, because we say like, you know, it could be more than just one specific thing. For example, we're talking about heads and tails. It could just be flipping heads or flipping tails, which would be more like a point. But you can have multiple points. You can have a spectrum of events, and that's how we kind of make it generalized. So we can have like obviously A and B right here, but we also could have easily had something like, how would we draw it another color? We also could have intersections like this, right? Where the events in C that happen and the events in A's that happen, they can occur in both. There's this intersection part in here. And this is when we start getting into like different ways of doing calculation. Basically, you can think of like the rest of the stuff that we're going to talk about. It's like counting, but counting with area. That's kind of like what's going on. So we can say something's independent, and we kind of know the general idea probably of what independent means. Like obviously, I think the curriculum talks about a factor where your mood in your the weather, those might not be independent, but like something like, let's say, I'm trying to think of a good example, like the weather. No, your mood and someone in China's. in a season, maybe. Like, it's kind of
Seasonal
weird.
affective disorder, right?
It's hard to say like something's independent because like I always think like in the very high parts, like everything's connected in some way, if that makes sense. Like technically you breathing is like connected with the weather. So like
Oh, I thought you wanted it to be connected. I'm sorry.
oh no, yeah.
I'm gonna
If I
stop.
want to do something independent, but like you can think of it like, oh, if you do this one thing, like flipping one, like if I flip a coin here and Paul flips a coin where he is, they're probably not, they're not going to be dependent on each other, right? Like they're not going to have that dependence. And you can think of that, that's an independent event. Or you can even think of like multiple coin flips. If I flip the coin multiple times, each coin flip, we ideally would be independent of each other. Okay. One coin flip isn't going to affect the next one. And again, this is where I'm kind of like in my head, I'm like, oh, technically that's not always true, but it's such a small degree, it doesn't really matter. Okay. Hopefully that doesn't confuse you guys. But anyway, we can start talking about these parts. And so we actually say, like formally in the mathematical language, something is independent when we have one, basically the intersection of A and B is equal to the probability A and probability B, or times those parts. Okay. And so you can kind of think of that like when you actually have the intersection of those two parts, what does that mean? These actually turn out to be equivalent right here. Okay, so I'll talk about the next part because I think this one's more obvious. And so this is probability of the A union. That's what that kind of weird, kind of like almost U, and there's an upside down U that we're going to see over here. But basically the union of A and B is equal to the probability of A plus the probability of B minus its intersection. That's what that upside down U means. Okay, so the way I would draw this out is that, and I think the curriculum does a good job kind of showing a little bit, is that the A union B, if I have A and this is B, right? So I have this part, and this is right here would be, this total thing would be its union. So this whole shape. So that would kind of look like, if I were to draw it out separately as one big blob, that would be like the union of it, right? That's the union, okay? And then you can talk about the intersection for that same thing. The intersection, we'll just draw as an upside down U. That's kind of like the notation for mathematics. It's just this part right here. So you can imagine it's just like this little gunk right here. Okay. So what this is really saying is saying, hey, if you take the union, take them all together, which includes this part right here, right? This should be, they're independent when you take the union and you say, okay, that is the same thing as saying probability of A, right? So I'll draw this out differently. So you can think of like probability of A, which is that circle. I'm not going to draw it perfectly, right? And the probability of B, right? But then minus that intersection, excuse me, that intersection, that should be equal to just the union, which makes sense. It's like, okay, we're basically, if we just took the probability of A and B, there would be this extra part, right? We'd get this extra intersection part because we're counting it twice. And so we subtract off that intersection part. And that's how we say, oh, they're equivalent to each other. And these are actually what's going on here. And I could have written this as probability A, or probability of A intersected B is equal to PA times B. Basically, they don't affect each other. So the intersection in between that two. You're just saying this will happen. So you can think of it like the probability of getting heads and then heads again. It's just the probability of heads times the probability of getting heads. Or if I had something like the probability of getting heads and then tails, okay, would just be basically the probability of getting heads times the probability of getting tails. And note, there's kind of a subtle point in this being independent because multiplication is commutative, right? I can just like switch these around. I could do the probability of tails times probability of heads. Those are the same kind of things. So that kind of allows us to do that part. And that only happens in independent. If it's not independent, right? Like if me flipping heads somehow affects my later flip of flipping tails, then obviously this won't work. And obviously I can't swap them around too. I can't do tails first and then heads and get the same probability as heads and tails. But of course, most coins work independently. Okay. Any questions on this, on the notation? I'm trying to like just kind of give you guys a visual of like what the mathematics is showing. And that's really what mathematics is. When we write all this stuff down, it's just trying to formalize it and just make it, what's called, it's summarizing some description of the world. And that's what we're doing here. Okay. All right. And then last one we have is disjoint, which will come in play when we talk about, you know, different probabilities. But disjoint basically is like when the probability of the A union B is just equal to PA plus PB. There's no crossover. So if you imagine if I had, some crossover like this, if I added together the probability of A and the probability of B, it's like the area in here, I'd get twice as much. I get this extra little part in here. So this would be disjointed because they're not touching. Like A and B here would be disjointed because when I added up those probabilities, that's the total union. There's nothing extra, right? But A and C, if I did the union of all of A and then all of C, I'd get this extra part right here because it's double counted. Okay. So again, these are just important things just to understand. And then right here, I wrote down his probability of A given B. We'll write this like this guy. And this will come and play a little later. But we'll say when you see this A and then that line right there, B, you can read this a couple ways. You can say probability of A given B. I've also seen mathematics, there's less of probability, but you'll say A such that B. So basically it's saying that what's the probability of A happening if we say B happened first? And that's the kind of stuff that we're talking about. And you can look at this and you later on, we'll basically say oh, this actually comes directly from the fact that P of A intersecting B is just equal to P given A, or probability of A given B times probability of B, okay? And you're gonna see this kind of swapped around quite a bit, okay? And you'll see it just come right from here. And this is just a theorem, basically. It's a rule that we say, this is true, okay? So this kind of leads us to a few theorems that, well, first of all, does anyone have questions on anything about this theorem's part? Notation, anything like that? Okay, cool. And sometimes too, I think, if you are feeling kind of iffy on it, I think definitely kind of going through it and kind of reading it through and kind of saying, what would this look like is helpful, because then you can see it both ways, okay? So this kind of leads us to a few theorems that we have for the mathematics of probability. So the first one's the product rule, which is kind of it's the equivalent to how we do multiplication, right? And so, excuse me, this is our probability of A and B. And this is just equivalent to saying, okay, that means that's probability of B, right? But times the probability.
Sorry to interrupt. Could you zoom just maybe a little bit? It would
Oh,
just
is it
be a little easier
guys?
to see.
Yeah, sure. Let me
Appreciate it.
that. Okay, is that better?
Oh, that is awesome. Thank you.
Okay, cool. Yeah, I know these small formulas probably aren't the best right now. So, okay, so hopefully that figures are able to see things earlier. But where was I at? Oh, this product rule. So when we look at this product rule right here, all this is basically saying is the probability of B, right, times A such that B happens, okay? And this is basically the A union, intersection of B. So we can talk about when A and B happen like this, right? It's just saying that's okay, the probability of B happening, and so this is B right here, times the probability of A such that B happens. And that's kind of like this guy right here. And that ends up giving us the intersection. So basically it's saying how likely is B to happen first? And then how likely is A going to happen such that B? So basically you can think of it like saying this probability right here, A such that B, is kind of like saying of this total part right here of B, how often does this happen? Okay, that's what this is really saying. This probability A such that B. And it's saying, okay, how likely is this going to happen in this sample space right here, in the sample space of B? And then we say, okay, going out one further, probability of B, how likely is B going to even happen in the probability, or in the events, or sorry, sample space? So in this whole section right here. Does that make sense? So it's kind of we first start off with that probability of B. We first say hey, how often does B actually happen? That's our PB. And then we say into here, probability A such that B, we're saying, okay, given that we have just this sample space of B, we basically say, just look at B, how often does A happen, that intersection part? And this gives us the intersection, which makes sense. We're just looking for this part right here in the whole sample space. That's what's saying, oh, you need to find out how often B happens, and then say how often does A happen when it's inside of B. And then you'll notice that it goes the same way since we can go reverse. Note that if this is disjoint, well, okay, what happens if A and B are independent? What would this kind of end up looking like? I want you to kind of think about that a little bit. But this is actually in the curriculum. Kind of keep that in your mind saying, well, if A and B are independent, what would that end up looking like? And I'll just kind of give you a hint is that if you think of this part right here, we actually have this part right here. And basically the probability of A such that B happens, you'll see that it ends up being just A. So it's like the probability of A happening such that B, they're independent of each other. It doesn't matter. So it doesn't matter whatever B is. If B is only 0.00001% of the time, but we have it so that they're independent, then we just have to care about the probability of A happening. So again, it's in the curriculum too, so you can take your time to do that. But you can see at least mathematically where this kind of comes from. It's saying, oh, okay, if we have this part right here, it just ends up being the probability of A, because we don't really care about, because like probability of A happening given B, well, it doesn't matter what B is. A is going to happen regardless of, you know, what B is. So this is just the probability of A. And that's where this comes from, why we can actually say it kind of goes back and forth. It depends how you want to proceed forward, how you define, and we define it by independence here first, and then define everything else. Okay, cool. All right, so that's one of our major things is our product rule. So we'll use this quite a lot when we're trying to figure out, like, you know, okay, what happens when this happens, like given this. The next part is our chain rule, which can be kind of cumbersome, to be honest. And the curriculum shows like the more general rule with like, what's it called? Like summation, not summations, but like basically going like sub indexes and stuff like that. And if you're doing like those parts, that's when it can start getting like really big. But basically it's like if we have multiple intersections for this guy, we can basically break it apart. So we're like, okay, we can look at probability of A such that the probability of B intersecting C times the probability of B intersecting C. And then you could break this down further and then break this down further. If they're disjoint, it ends up being kind of nice because then you can simply get like these parts right here where C, if you imagine if C is disjoint, so this is like usually how it's drawn out, like if this is, let's say this is all of C, so you can kind of think of, this would be like C1, there's C2, there's like C3 and C4. It's like C4, C3, C2, and C1. Note that I wrote it just all connected together. That's just to like give it some visual. It doesn't have to necessarily literally be like in that way. And again, these shapes are just arbitrary. There's not like a real reason or anything like that. It's just kind of showing the idea of like you can have a collection of points. Okay. And just know that C1 and C2 don't overlap. So the probability of A basically it's just saying, just look at the probability of C, probability of C, probability of C times A. Okay. Cool. Okay. And then definitely look at the curriculum, this part. To be honest, we probably won't do this too much where we're like trying to chain it together, but this is useful when we're trying to figure out the actual probability directly from what we're looking at. The mathematics just helps us condense it down so we can just basically not think about the individual cases and just look at the single probability mathematically. Right? And then this next one is probably the most like, I'd say like the big, like people say like this is like the biggest thing, like, you know, Bayes theorem and our Bayes rule. And this is kind of like this association which allows us to update our probability as we go through. So basically it says like, hey, if we want to know how often A happens given that B happens, all we got to do is figure out, well, okay, how often does B happen given A times the probability of A times probability of B. And we give them some special names. So the prior is PA. It's kind of like something that we already know. The posterior, AB, is usually something that we like want to know. We're just like, hey, like how often does this happen? And then BA, you can kind of think of like how likely this happens. And usually this is something we measure. We'll like measure in some way of like saying, hey, you know, let's take a bunch of people, for example, how many alcoholics have liver disease? That would be something like that. So basically the probability is like, hey, how likely are you to have liver disease given you're alcoholic? Okay. And we can use that kind of stuff to basically figure things out. And this is really nice because we'll see, this is for Bayesian learning. And this is one of the machine learning techniques that we'll use. This is basically the basis of that machine learning technique and allows us to kind of pop in, basically try to figure out what the probability happens based on what we've measured already. So that's when these event spaces really are helpful. Okay. We'll talk more about this one too. I didn't want to go full detail on this one just because we're going to use it again, and I'd rather go into detail then versus go into detail now. Of course, the curriculum does start talking a lot. Like there's a whole section dedicated just to Bayes' theorem, or sometimes called Bayes' rules or Bayes' theorem. But it's something I think we can talk about more when we go into naive Bayes, when we actually do some of the machine learning aspects. But if you're curious, it's in the curriculum, and so you can start looking at that now. And I think you should, but we'll talk about it again. Right. So the last thing I wanted to bring about this is on partitioning. So one thing is that we can do is like the curriculum kind of shows that one strategy we can have. Sometimes it's hard to measure the probability of event space A happening. And so, for example, the curriculum has some similar thing like this, where we have the probability, or like this is the event space, or yeah, the event space A. And then I think basically we take partitions, which just literally just means cut these into parts. And it's like, okay, we can measure when C happens, or let's say C1, C2, and C3 happens. And this might be easier for whatever reason to actually say, hey, let's measure all of C and how often A happens. And say, okay, let's measure all of C2 and see how often A happens. And then C1, figure out how often A happens when C1 happens. So this allows us to like basically make those parts, and we can actually use these theorems up here, the product rule, the chain rule, to build A, even though we can't, for some reason, if we couldn't measure A directly. So this is just another tool. When you hear partitioning, just know it's partitioning the event space or the sample space. Okay. And again, they talk about some more, and they show a lot more of the like notation, but it's pretty much using all the same notation like we've been using up here. Okay, cool. So that's kind of like all of conditional probability. Just a real like quick, like high level, like saying, okay, these are all the different things that you're gonna look out for. Big things I would say, like, if you want to make sure you're like, okay, in the curriculum, like what things do I need to really focus on? I'd say Bayes' theorem is something that we're going to talk more again, and what exactly this means. So just kind of be aware. It's like, it very quickly says it in the first section, and then there's a whole section about Bayes' theorem, but we're going to go a lot more into it. This is more like not what Bayes' theorem is, but more like saying what the mathematics look like. But I think we should go more into like why does Bayes' theorem work and why is it useful? Just kind of know that. But the big one, I would say product rule. Understand that you can basically get the intersections using this formula. And then understanding that like you can write down disjoint and independence as actual mathematical formula. So then that way we can formally describe independence. When we say something's independent, we know these can be applied. Or if it's disjoint, we can apply this truth to it. And so that's kind of like the stuff, like I would say, just know that that exists. To be perfectly honest, you probably could like derive this pretty quickly when you think about it, like they're actually drawing out the areas. You're like, oh, the union of A and B, if they're disjoint, it's just going to be just A and B separately since they're not connected together. So I just think it's a good thing to see what all the mathematics look like. Okay, cool. Any questions on this stuff that I have? Okay, cool. All right, so let's see here. Yeah, so this leads us into parameter inference. And so this one is a big section. So just to kind of look ahead and learn in the curriculum. Yeah, section 21. So you can kind of see like introduction, conditional probability. That's like kind of like what I was showing you up to, what's it called? Partitioning, and then even to Bayes' theorem. That's kind of like this first section. I kind of summarized the whole lot for you. But let's see here. If I would kind of show you guys just what the mathematics look like. This is where, sorry. This is like, it's showing, it will show you a whole bunch of these images with like the actual equations. Hold on. So you can see kind of a similar graph from right here. And this, I think this is a great one, for example. This is just the union and showing this part. But you can see like this mathematics here. I just wanted to introduce you guys that. So when you guys read this, because sometimes the curriculum kind of just like, here's the equation. But like, if you don't know Mathanese, it's kind of a little difficult to kind of wrap your head around. But anyway, going further into this part, just read that through and you can kind of see the similar stuff. And they're just proving some stuff. It's mostly mathematic based versus like saying how you'd actually use this. Okay. And again, this is what I was talking about with like multiple parts. So just I think they messed up on, well, they didn't mess up, but when they say A1, you can think of A sub 1 or A sub 2 or A sub n. So they're showing those parts. Okay. All right. So I just wanted to show you that really briefly. But going back to this part, which is parameter inference, this comes from the curriculum from right about here to here, which seem really short, but they're really important aspects. And I think this is the stuff I'm going to focus on for the rest of the time, because I think these are really important to understand, like, why are we doing this and how is it working? So we're going to talk about that. So the first one is our maximum likelihood estimation, called usually abbreviated MLE, just because that's a mouthful to talk about, right? And basically, it's a way to infer what the parameters are for a model. So we'll use this in our machine learning models when we're doing more predictive learning. And we're saying, like, you know, what kind of things we'll use? We'll use the maximum likelihood estimation to see basically what events likely to happen, okay? And so there's a couple assumptions that we put in here. The curriculum notes that it's sometimes noted as the IID assumption. Basically means independent and identically distributed. We'll talk about what those mean in a second. So obviously we talk about independence. Events have to be independent from each other. They're not, one thing's not affecting the next one. And again, you can always think of like I like to always say, like, nothing's really independent when you like really think about it. Like, it's like, oh, the world's never really independent. But to approximation, we can always say, well, okay, does it actually affect this? Like me flipping my coin, you know, and flipping another coin isn't going to affect each other directly, at least not to a degree that would make sense, or that we would care about. We can use this independence assumption. And sometimes even things that are not quite independent, we can still use these assumptions. But again, this is why it always comes down as like your data, like what does your data represent? If your data are about things that are like strongly dependent on each other, then you have to be aware of that before applying any of these rules. That's why we always take this part and say, hey, is it independent? Okay, but this is required for MLE. Okay, and then we also say it's identically distributed. And what that basically says is that each event has the same parameters. Basically, is that the event, like, you can think of it like flipping a coin. That's how I kind of imagine it. If you flip a coin once and then flip a coin 100 years from now, the parameters shouldn't have really changed. The probability of getting a heads or tails is still 50-50. But something could change in the sense of, like, let's say if you flip a coin, and then as you're flipping a coin, this is something ridiculous, but as you flip the coins, someone grabs it and always puts it down as tails. Well, now they're no longer the same parameters. Those two events are no longer using the same parameters in that sense. They're not identically distributed, okay? And so we'll use this parameter as like theta, okay? And so I wrote this out really quickly, like this is the summarization from curriculum. But basically this just comes with the fact that it's like the probability of an event times the probability of the event times the probability of the event, right, is equal to the full probability, okay? But we'll use this notation right here, and this actually comes, I think this comes directly from the curriculum, is that this symbol right here, which looks like is actually a capital pi. Okay, so usually we talk about like lowercase pi like this, right? This is a capital pi. This thing is basically just saying, it's like a summation, but instead of summing it where we're adding it together, it's like the product. It's saying, oh, just multiply all these parts together, okay? And this, again, kind of like a summation, it goes from I starting at 1. So we say, oh, the event number 1, and then count up to n events. So, you know, if we had like 4 coin flips or 10 coin flips, that n would be 10, okay? And then the probability, you know, P is just probability, right? But you see the probability of I, so we're doing a specific probability. We probably, like in realistic terms, we probably don't need to put this I right here because it's just a probability, but just know that that's what the curriculum kind of uses. And then I will use a slightly different notation. I think it makes more sense, and like when you think about it, is we'll have this E, so this event space E, and that event is equal to a specific event EI. So for example, if we had just heads and tails, EI would either be heads or tails. So what's the probability of the event, let's say heads, happening such that this parameter right here, this sigma I, okay? Sorry, not sigma, theta I, okay? And so because they're independent, because they're identically distributed, theta doesn't change. Basically, theta is like the parameter, so like given that these parameters, okay? And let's see here. That's the main thing. And then independence just means that like it doesn't matter what the like it should be the probability every single time of this event. So it doesn't matter if we flip heads and then later on flip heads later on. That probability should be the same. Okay. Cool. So that's the notation right here, and I just kind of wrote it. And here this is what you'll see it summarized as. But just note that capital pi is just being multiplied together. And that theta is the parameters. That's really what we're saying right here. Okay. So what we want to do is basically find when on this function right here, which I called later f of theta, this function right here, we want to find the critical point and test for the maximum. And so the critical point is basically just saying when is it max or min. Okay. And we actually do this from like we talked about way back when we did derivatives. We can use derivatives to find what's the maximum or when the maximum or min happens. But the thing is, because the first derivative doesn't tell us if it's maximum or minimum, it's just called the critical point. We have to do a separate test for if it's maximum or not. So you can kind of think of like any function, right? Any function like looking like this. Okay, we can actually find like, okay, like this is just if this is f and this is theta. Okay, we're just traveling along here. We want to find the maximum. So obviously, if we just looked at the picture, we say, oh, it's like right about here-ish. Okay, but we want to figure that out. And so one quality that this has is the derivative, is that we can actually use the derivative to help us find when it reaches this point of maximum or this point of minimum. So if you notice right here, and I'm going to extend out this original one just to kind of prove my point. And I'll just assume that goes on forever, like straight. Okay, so if we're trying to find the maximum, okay, we can actually see when the derivative changes to 0. So like when anything goes up to a maximum, okay, and you can prove this in calculus, but we're not going to go through the whole proof, but you can kind of visually see that. It's like right here, the derivative, well, what's the derivative right here? If I looked at this point, is it positive or negative? Remember, just derivative just slope. So is the slope positive or negative in this case?
Positive.
Positive, good. And I saw Jonathan point up, right? So yeah, positive, right? It's going up, it's increasing, right? And then as we go up here, you actually notice that is the slope smaller or bigger right here? It's smaller, yeah. It's a, I'll go, yeah, smaller, right? So the derivative, remember, I just think derivative is the same thing, is that the derivative is getting smaller, and then it gets smaller and smaller. And the idea is that over here, we can see the derivative's changed, right? It's now negative. It's going downward, right? And so we can say there must be an in-between part when it went from positive to negative. And so we can actually say, oh, well, that means there's some point right here where the slope is 0 or our derivative is 0. And that's what will bring us to here. And that finds us our critical point. But here's the issue, is that we say, oh, when the derivative is 0. The problem is we could also have a minimum. So the minimum could have the same thing where we have a negative going for first, and then it switches to positive, right? So when we have that, that also gives us a derivative of 0. So this is why like the first derivative can't actually tell us if the point is maximum or minimum. It just tells us it's at 0. And there's a third option. Does anyone know what the third option is? That will still give us a derivative of 0, but it's not a max or min. Yes, this is a fun one. It's your inflection points. So if you have something like this, it goes up like this. It's not really a max or minimum, but there's this point right here where the derivative is 0. Okay. So that's something, that's another critical point. That's why we call them critical points. Okay, but usually we're not going to, hopefully we're not going to get this. We're going to use the second derivative to actually figure out, hey, is this thing positive or is it a maximum or minimum? And so remember just df of d theta. So basically taking the derivative of f with respect to theta. And you guys can see that okay? Not too small. Okay, cool. We're basically say set that to 0, and this is going to be a function. So like, for example, I think the curriculum had something like, you know, theta to the power of 6 times, oops, I did that wrong. 1 minus theta to the power of 4. You would take the first derivative of this with respect to theta, basically treating theta like x, like you normally would as a derivative, and then figure that out and then say, hey, set that equal to 0. So you take the derivative of this whole thing with respect to theta. Figure out what that function is, whatever that derivative is, and it'll be some form of theta. And then we solve for theta by setting it equal to 0. And whatever theta gives us, that's our critical point. Note that we can also get multiple critical points. We can get like multiple ones just like this one. If we gave a function that was like this would give us multiple critical points. And we have to figure, okay, which one of those are maximum? Okay. To figure out if they're maximum, what we can just do is take the second derivative and just see if it's greater than 0. Okay. And really what this is saying, like at a higher level, is like, why do we take the second derivative and say it's greater than 0? Like, what's going on? Basically, if you take the first derivative, you actually are drawing out not f, but the slope of f, right? The derivatives of f. So basically what happens is that we're saying on the second derivative, we're saying how does the slope change? So does the slope go from positive to negative, or does the slope go from negative to positive? And then we can even test out if it's an inflection point. But basically the important part, because we want to find this maximum, basically we want to see the second derivative at this specific point. Okay, that's what this, you'll see that line and then sigma c. Sigma c is our critical point. Okay, we basically say we take the second derivative, we'll get a whole like value, or not a value, a whole function. We plug in sigma c into there and say, is that value greater than 0? If it's greater than 0, then we're good, it's maximum. Okay, cool. And that's just our calculus part. All right, and then once we have that, then we know what the critical point is. Cool, awesome, right? Now, the thing about doing this guy right here, your first derivative, and then obviously you have to take your second derivative too, this can be an issue. Not an issue, but like it's cumbersome. It's a lot of work, right, to take all these derivatives. So one way we can do this, and you'll see this a lot in probability theory, is that we can do a kind of a shortcut, but basically say, let's just take the log, like the logarithm, you know, of the probability of this function f, okay? And the reason why we can do that is because what we're trying to do is not actually trying to find what the value of f is at that critical point. We're just trying to figure out what is the critical point. Like what, I'm sorry, not the critical point. What is the maximum in that function? And because if we do a transformation with log, it's still going to have the same, like, what's it called? The same position of theta. It will have a different value, like the log of this function versus the function. We plug in, let's say the maximum is like, I'm just making a number, 3.2. We put 3.2 into their function. That f of 3.2 is not going to equal the log of whatever f is. So like f of 3.2, let's say it's giving us like, I don't know, like 2.7. Okay, then that means the log, the natural log f of 3.2 is obviously not going to equal 2.7, right? It's going to be closer to like 1 or something. But like the point is that it's going to give us a different kind of value. And it doesn't matter though, because all we care about is finding 3.2. We just want to find the maximum value. So we're saying, hey, let's make it easy on ourselves, because it turns out if we have logs, we can take the derivative really easy. So does anyone know what the first derivative is of a log function? Oops. Jeez, I can't write today. There we go. So I have a derivative with respect to theta of something that's like log of theta. And no, I'll put log or ln. It doesn't really matter what we're doing. Does anyone know what the derivative of that is? Really easy. It's just 1 over theta. Okay. And what's kind of cool is like if I replace this with a function then, right? If I say a function of like h, it's just 1 over h times the derivative with respect to theta of h. Okay. So that's kind of nice. It's like, oh, this is actually pretty quickly, we can write this out. And it turns out because probability tends to be just based around theta, we can just do like of, what's it called? Of theta over here. And so kind of give you an example really quickly that I'll show you what the curriculum shows, because I think that's probably just the easiest way. Oh, that's not what we want. That's not what we want. That's what we want. Okay. So kind of going forward, I'm just zooming through. So this is our function right here that I was talking about at the very beginning. They'll use a lowercase p, but I use a capital P. It doesn't really matter. And that f is like a capital E for me. They have 2 possibilities. You flip a coin, you know, heads or tails, okay? We can say, oh, theta basically, we don't know what the parameter is, but let's say the parameter for heads is just theta. Okay. And then to get tails, there's only 2 options. We can do this 1 minus theta, right? So basically you can write as say, okay, heads, heads, tails, 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 heads, 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 okay? And we can write out this function. they're just all being multiplied together. That's the probability. And we can just say theta 6, because basically we're just getting all the thetas, then 1 minus theta 4. So basically they're just grouping all those parts in there. Basically, how many heads, how many tails, okay? So it's kind of nice though, when we have this equation, if we had to do the whole, like, you know, with the derivative, we'd have to do like, okay, theta over to 6 and the 5 and like put those all together. Well, it's kind of nice if we do the log of that, we can actually just say, hey, the derivative of that function that we just had up there, but taking the log. So like, you can see right here, this would be our, we're trying to find the maximum of this theta 6, 1 minus theta 4. This is just f. If we take the log of that now like this, that ends up being just, hey, 6 times the log of theta, and then 4 to the times the log of 1 minus theta sigma. They're taking basically they're just taking the derivative up here. You're taking that function part out. They're using the chain rule, right? And then once you have that, you can say, hey, what's the derivative of log of theta? That's just 1 over theta, and then times 6. And then what's the what's it called? What's the derivative of log of 1 minus theta? Okay, that's 1 divided by theta times -1. Basically, that negative, the derivative of this guy right here with respect to theta is just -1. So this comes out right here. And then you'll notice that they'll have h and t here, because that's just the 4 and the 6. Basically just how many times that happened. In this case, we had 6 heads, so it raised to the power 6. We had 4 tails, power of 4. So we just get this number right here. And now we have something really simple to actually write out. And we don't even have to take the derivative anymore. We can just simply write this out. Say, hey, how many times does this event happen? What's the probability of that? Just 1 over that probability, or at least 1 over the probability times its derivative. And then we can do that part. Versus like having to do this whole thing and then try to do that and then try to form it. This makes more sense. And usually we'll do this trick where we'll have like things multiplied together. Mathematicians love taking like the log of it, because then we can just do it summations. And summations are usually a lot easier to deal with than it is for products. So just know it's like a quick shortcut. Okay, and that's what's going on here when you go through. One thing to note though, I have this argmax, or they have this argmax here. I wrote it down here too, is that all that is saying, it's kind of like, I like to imagine it's a fake function. It doesn't actually exist. There is no function that can tell you how to do argmax. Like it's not like, oh, like sine of like x. It's not like you take this thing and say argmax on your calculator. This is just saying a mathematician's way of saying, hey, I want to find what is the maximum argument. Basically, what value of theta gives me the maximum value. That's what it's saying. But in reality, what you're doing is you have to take the derivative of that function, in this case of g of x, and say, okay, one is set that equal to 0, find the critical value, and say, hey, is this critical value actually the maximum? That's really what's going on here. But what's kind of like, they kind of do a little shortcut where they say, hey, they're taking the arg maximum, but since we already know we're going to take the derivative, we can say the arg maximum of this function, which is almost halfway through the derivative. And that's why it's able to use that kind of notation. But just note, whenever you see this argmax, it's just saying, like mathematicians speak of saying, hey, you need to find the maximum argument of this value. But the process of doing that is just not a simple plug and chug. Does that make sense? Okay, cool. Again, main thing is that you're trying to find the maximum value of theta, and this is a nice shortcut. Okay, you could do it this way. There's not like a reason why you couldn't do it this way with the function here. But since we're going to do it at the same time, probabilities are always going to be multiplied. If you take a log, it just means we get a summation instead of a what's it called? Instead of a product. Okay, so that's kind of our guy. Basically, you can kind of think of it saying, oh, you're just taking the maximum argument of this function right here. Okay, and I think when I showed you, kind of showed you like here, they end up saying, oh, this is just our ending function, just the number of times. So again, you get a really quick shortcut. You don't have to do a whole lot of stuff. Okay, so quick things about, they put on here? Okay, yeah. Quick things I talked about are put on here, notes, limitations based on the data we have. If you only flip 6 times, like the curriculum shows, like if you only flip the coin 6 times and you get heads each time, you can't actually estimate the real maximum likelihood because you don't have enough events that actually cover the whole space. So just note that this maximum likelihood will not always be the right answer if you don't have enough data in there to actually cover all of the event spaces insufficiently enough. So that's kind of like one of the limitations you have to kind of keep in mind. But other than that, it gives you an idea. It's like, what's the maximum value to actually make this probability happen? So this kind of leads us into another one, which is the maximum A-Posteriori, which basically we'll call it math estimation, right? And usually MAP. And basically it uses Bayes' rule, Bayes' theorem, right? And it uses that posterior, okay, that I kind of defined earlier, is that we can use this Bayes' theorem, basically say, hey, we want to find the maximum of this guy instead. And so note that we start off with Bayes' theorem, theta such that x, and that's event x. And we can actually say, hey, this is proportional, because we don't really care about the exact value. We just say, hey, we're going to find the maximum. It doesn't matter if it's being put by a constant. And we can think of this p theta essentially as a constant, right? It doesn't change, right? Theta doesn't change at all. So it's just a number, and it doesn't really change. So we say, hey, let's just get rid of that. So we can say, hey, let's just get the maximum of this part right here, this px such that given theta times the probability of x, okay? So that's why they're saying ignore the normalization constant. So they're kind of looking ahead when you do this. And they say, okay, now let's get the maximum argument of theta based on this. It's like, well, we've kind of done this before. We can then just say, okay, well, let's just do the same thing as we did before. Let's do the logarithm, right, of these probabilities. So we're just kind of ad hoc and putting that in there since it's going to be the same way. And we can basically use this to determine, what's it called? We can use this to determine our theta map, our maximum argument, okay, for theta. And it turns out what's kind of interesting is that we actually end up getting the same answer as our MLE up here. We actually get the same answer, except we're just weighting it by the probability of theta. Okay, so I kind of want to show you just what the curriculum shows you. Oh, that's not what I want. Sorry, guys. Oh, it's right here. Okay, so you can see right here, it's the same as being weighted as this part right here. And so I just wanted to show you what the math kind of showed up on here. And again, they're just using more notation. I would definitely like kind of read through it. Oh wait, this is the wrong one. My bad, guys. Where did it go? Okay, sorry, clicking around too much. But I just wanted to show you what the curriculum kind of shows you. Is that basically you go from here, it's like, hey, okay, let's go ahead and take the arg maximum of that log value here. And you go through it, and you end up getting this guy right here, okay? The summation of our log p xi such that theta times probability of theta. But remember, we just had essentially this, the probability of theta right here, okay? We had this part right here, and we're just being multiplied, I'm sorry, not the probability of theta, probability of E such that theta happens. But this one right here is basically just being multiplied by P theta too, okay? So now we just basically have the same exact answer, we're just weighted. So if you look at this actually closely, is that MLE is just a special case of MAP where the prior is uniform. So it's basically like if we're always gonna get the same thing, like a die flow or throw or like heads or tails, this we can use MLE, it's the same process. But if it, for example, the probability of getting rolling two dice and getting like a 7 versus an 8 versus a 12 when you add the die numbers together, that wouldn't be uniform anymore. We'd have to think about what theta is in that case. But what's nice is that, oh, if it's uniform, then we can just say, oh, it's MLE. Okay, and that's just the difference right here. It's coming from here. But you approach it in two different ways. You use Bayes theorems first, or you basically start off with the fact that these things are identically distributed. Basically that it doesn't change between different aspects. You're going to get either heads or tails, 1, 2, 3, 4, 5, 6. Okay. So yeah, this is kind of, I wanted to introduce a little bit of like the math in there, because I think going in the curriculum, especially if you're not, you know, comfortable or like at least not familiar with like all the math notation, I think it can be really really intimidating. But overall, it's just explaining parts that are you're describing in your own words. Like you can describe it out loud in your words and then use mathematics to help formalize a lot of those parts. So just know that I think this section in particular, because there's so much, you know, mathematics, for example, it's going to like, you know, take some time just to read it through and say, okay, I see the math formula. What is this math formula saying? And then kind of going back and forth, okay? The big one I probably would say is like the argmax is probably the one that's most, like, at least for my mind, always kind of takes me like, wait, what's argmax? And it's just saying, essentially you're telling someone, find the maximum of this function, which is going to involve taking the derivative. Okay, cool. So yeah, that kind of finishes up what I wanted to go over. Of course, note that I didn't go over everything in the curriculum. The curriculum in this section is particularly dense. It's a lot of mathematical formula. My suggestion to you is not trying to memorize what these formulas are. If you're going to memorize any formula that given in here, Bayes' theorem is probably the biggest one where you'll see again and again that you should be able to call up easily, just because you're going to use it again and again, and it's super useful. But everything else, I would actually say you'd probably look this up. You should be familiar though, and say, if you look it up, because everyone has slightly different notation, that you should be able to look it up and say, okay, what am I looking at and what's being described here? So I would say it's not so much the formulas are important, it's what the formulas represent, and being able to look at now a formula and say, oh, we're talking about, MLE. Okay, what is MLE? And it's like, oh, okay, we're basically taking a function and taking the derivative to get the maximum. We're trying to find the maximum part in here. And that's what it comes down to. It's like, why are we taking a log? It's like, oh, we're taking a log because it's just a simple math shortcut. Okay, those are the important parts, I would say. Like, I wouldn't like hit your head against the wall trying to memorize these equations, because one, it's just that you're probably going to memorize it wrong. Like, that's just reality. Like, I know I have done that, where I'll remember like, wait, was it theta or a log, or where's the log in there? And like, I think that's really dangerous to do. I think it's more important to say, what does this equation supposed to represent? And then kind of logically thinking about the steps, and then looking at the equation saying, oh, okay, I can see where this comes from. Okay, cool. Is there any questions you guys have? Anything you guys are in particular like really stuck out and say, oh, like what about this or something like that? Yeah. Okay, cool. Thumbs up, thumbs down, sideways. Yeah, that's expected. Yeah, I went through a lot of stuff. I'll be honest, I could probably do a little bit better explaining some of those aspects too. And I know I kind of went through it really quickly, but as you kind of go through, hopefully the curriculum goes through, and then of course, ask questions. If you're like, I don't really understand what this equation is, or why are we doing this? Ask those questions, either to me, to your other peers, whoever, go search online. I think just kind of looking at it and seeing where the equations come from and what you're trying to do will help a whole lot. All right, guys. Well, I'll go ahead and stop sharing my screen. I guess I could stop recording too.